5.1. So 5.2 is pretty much going in the other direction. So we saw that the derivative of natural log u is u prime over u. So that means that this function is the function that has that as a derivative. So when we integrate, we're looking for what function has this as its derivative. Well, the function that has u prime over u as its derivative is natural log u. Now we have to be a little careful because the domain of natural log is a little bit restricted. What kind of numbers can we take the natural log of? Positive. So we can't take the natural log of negatives. So the way we fix this is we take the absolute value of u. So basically that's our integration formula. If we come up with a function whose integral is du over u, that's going to integrate into natural log of u plus c. Now, going back to a few derivatives, antiderivatives. If we had a function like this, the first antiderivative formula that we studied was the power rule. And the power rule says if we have x to a power and we want to integrate it, we do x to the one larger power over that power plus an arbitrary constant. We talked about with integrals or antiderivatives, really there's a family of solutions because the derivative of a constant is 0, so technically we could have plus lots of different numbers on the end, but our functional part is specific. So if we want to integrate this x squared dx, the integral of that is x to the one larger power over that power plus c. How do we check to see if that's the correct integral? Right. And an integral is a function that has this for the derivative. So if we want to see if this has that as its derivative, we take our integral and we differentiate it. So if we take the derivative of this, we can pull our 3 on bottom out front. The derivative of x cubed, that's just the power rule, 3x to the 1 less power, plus the derivative of a constant, 0. 3 on bottom, 3 on top cancel. So yes, the derivative of this is x squared, which makes this the antiderivative of x squared. This is the function whose derivative is x squared. That will work with any function that has x to a power. Unless that power is x to the negative 1. Because notice what happens. If we try to integrate this using the power rule, what is 1 greater than negative 1? 1 more than negative 1 is 0 over that power. So what's wrong with this? Can't divide by 0. So if we try to use the power rule for x to the negative 1, we have a flaw. When we do x to the 1 greater power over that power, that's undefined. So when we listed our integration formulas back in chapter 4, we said that the power rule worked for any exponent except -1. And we had a list of things that we could integrate. Again, in the front of your book, there's a tear out that lists integration formulas. Let's just review some of those. If we integrate a constant, we just pick up our variable plus an arbitrary constant. If we integrate x to a power, that's x to the 1 greater power over that power plus an arbitrary constant. Just like derivatives, if we have two different functions, we integrate each of those. But we don't have a product rule for integration. We don't have a quotient rule for integration. Now we can integrate some trig functions. What function has a derivative of cosine? Sine. What function has a derivative of sine? Negative cosine. Let's see. What function has a derivative of secant tangent? Secant. The derivative of tangent is secant squared. So that was going to be the next one. The function whose derivative is secant squared, that's tangent. So it's basically going the opposite direction of a derivative. The antiderivative of secant squared is tangent because the derivative of this is secant squared. And there are one or two other ones that we've already done. But that's pretty much it. Derivatives, we can pretty much take the derivative of anything at this point. We can do products, quotients, things to powers. Let me be careful with that. We can do the derivative of lots of things right now. We haven't got to the derivatives of logs, exponential functions, and inverse trigs and some things like that. But basic polynomials, rational things, we can take derivatives of about any combination of those. Our list of things we can integrate, though, is very small. In the grand scheme of things, once we get a little bit further, we can take the derivative of almost any function that you can write. It might be extremely messy, but you can differentiate pretty much anything. But it is pretty simple to write a function that you can't integrate. There are a lot of functions that you can't just sit down and come up with a function that's an antiderivative. Ones that we know how to do so far. And then we add to that today that, or sometimes you'll see that u to the -1 du. And that integrates into, as we said, natural log u plus c. Now, the key to this is going to be most functions that we have are not going to look exactly like one of these or exactly like that right off the bat. So we're going to have to do some type of substitution to take our problem and write it into one of these formulas. So what do I mean by that? If I want to integrate 2x dx over x squared plus 1, that doesn't exactly look like any of the formulas we have. That's a quotient. We don't really have, quote unquote, a quotient rule for antiderivatives or integrals. But notice that this degree is 1 less than this degree. So let's try letting x squared plus 1 be u. So if we want du, what's the derivative of x squared? 2x. And we'll do this formally to start with, and then we'll... If we were to take the derivative of this with respect to x, du over dx is 2x. So du, if we move the dx over, is 2x dx. So we need to take what we have and do a change of variable. We want to change this into u's. Well, notice this part is u. Is that du? Yes. 2x dx is exactly du. X squared plus 1, that's what we called u. That's one of our formulas. So we've taken something that we didn't have a formula for, we did a substitution and changed it into something that we can integrate. And what do we say the integral of this is? Natural log, absolute value of u plus c. Remembering that what was our original variable? Yeah, our original variable is x. So we want to, now that we have our antiderivative, change things back to x. So u is the same thing as x squared plus 1. Perfectly fine to leave it like that. But do we really need the absolute value on this one? No. I wouldn't count off if you left them on there, but often the book or WebAssign will drop the absolute value. And why would they drop the absolute value? Right. X squared plus 1 can never be negative. If I square a number, that's going to be positive. If I take a positive and add a 1 to it, that's positive. So while the absolute values guarantee that this is always positive, that's always positive anyway, so that's unnecessary. So the biggest thing there was we took something that didn't fit a formula. We made a substitution to change it into a formula that we had. The trick will always be, though, picking the correct thing to be u. So that once we find u, and then we find out, okay, if this is u, we call that u, we've got to get rid of the x. So how is dx related to du? Because if we have a u, we have to have a du that goes with it. So we can't just simply say, well, in place of dx, I'm going to change that to du. We have to know how those two things correspond to each other. Well, if this is how u and x are related, to find out how du and dx are related, we simply take the derivative of both sides. So du is related to dx, and that du is 2x times dx. those of y'all that had me for Cal1, we discussed that as long as we have the variable to the correct power and the dx here, we're good. If we're missing this number or if we had the wrong number, we can fix that by multiplying or dividing by some constants. But what we can't do is fix it if we're missing a variable or if we have too many variables. What do I mean by that? If we had almost that same thing, if we said u is x squared plus 1, which would make du, well, if we call that u, then what's left, that has to fit our du. So we need x dx. But we have too many x's. We have x cubed. So as it is, we can't just change that to du over u. All right, let's do another one. Let's do one thing. All of them won't be this obvious. But in the formula, du over u, basically the numerator is the derivative of the denominator. If you think back to the derivative of natural log, the derivative of that is, that's the denominator, the derivative goes on top. If I take this, what's the degree of this? 3. If I take the derivative based on the power rule, I'm going to drop the degree. What's the degree of this? 2. So if we have like a polynomial on top, polynomial on bottom, if this degree is 1 more, then there's a good chance that we want this to be u, so that when we find du, it's this. If we take the derivative using the power rule, we should be 1 degree less, which could be that. It could be off by a constant or so, but let's just see. So if we let the denominator be u, what's the derivative of x cubed?
3x.
The derivative of the second term? Derivative of a constant? 0. Yes.
Factor of 3.
Could do that. Both of those have a 3 in them. And if we factor that 3 out, notice that in our problem we have x squared plus 4x times dx. Well, that's almost exactly what we have here. So what are we missing in order for this to be du? We also need a 3. So we can multiply this by 3, but to keep it balanced, we have to put a 1/3 out front. Notice a 3 on top, a 3 on bottom, those cancel each other out, so it doesn't make it something that's unequivalent to what we started with. We're basically multiplying by 1, 3 over 3. When we do that, we have a 1/3 out front. We said that all of that is du. The denominator, that's what we called u. Well, that's something we know how to integrate. What's the antiderivative of du over u? Natural log absolute value of u plus c. So what is u? X cubed plus 6x squared plus 5. Now this can be negative. If I let x be, let's say, -10, then I'm going to get -100. I'm going to have more negatives than positives. So to guarantee that I have a positive quantity here, we do x squared plus something that's always positive. Now, brings up interesting point. If we had something that came out to that, would you need absolute value for that? Yeah. That can be negative. How can that be negative? Yeah, you had a 1, a 2, a 0. There are numbers that you could plug in for x and make that negative. So to guarantee that it's positive, you do have to have the absolute value. But if it's a plus there, that can never be negative. Any number I pick for x, when I square it, that's positive. If I add a positive to any positive, it will be positive. Kind of a rule of thumb, if you're not sure, leave the absolute value on there. It's better to put them on there and not need them than to take them off and, oops, I forgot a case. Now, with derivatives, while there are plenty of derivatives that are complicated, derivatives in general are straightforward in that once we look at the problem, it's pretty much going to be a chain rule, a product rule, a quotient rule, one of our special derivatives like trig derivatives, natural log derivatives. Integrals are not always so obvious. It's not always obvious what we're going to let be our u. For example, this. If that was something we were taking the derivative of, I could look at it and I could tell you we have a quotient, and in the denominator we have a product. But most of us might not be able to look at that and say, oh, I know exactly what I need to substitute u for. Any ideas? For those that have done this problem before, or that if you sat in while we've done the section before, also, you might pick it up. And some people that have never seen it, if you're clever, you might pick it up too. But if u is natural log x, what's du? 1 over x dx. Notice if we break this up a little bit. I gotta have my volume on. No, I think I'm still, yeah, I'm recording and I don't think I have to have my volume on to record. Okay, so if we break this up a little bit, let's put the 1 over x dx over here. Natural log is on bottom, so let's Write it like that. Isn't this equivalent to what we had? We have, if we were to multiply that out, we would still have 1 on top. On bottom, natural log x times x is x natural log x, and then we have our dx. Well, natural log x, we called that u, and all of that is what? All of that is du. Now, we could leave that as 1 over u du, or we could call that du over u. Either way, what does that integrate into? All right. Du over u, natural log absolute value of u. So it's a natural log absolute value, and what do we call u? Natural log of x. Now we do have to leave the absolute value because natural log, we can't take the natural log of a negative number, but we do get an answer that's negative when we take natural logs. So that's our antiderivative. Now they add some more integration formulas in this section. I'll give you an example of one that they add. This is something that we didn't have an antiderivative formula for but prior to this section. But notice that tangent is sine over cosine. And if we're clever by what we picked to be u, let's let our denominator be u. Then what does that make our denominator, our du? What's the derivative of cosine? Negative sine. So if this is u, then the rest of it needs to be du. Well, we almost have that. What are we missing? We're missing a negative. Well, don't two negatives make a positive? So those cancel. If I put a negative there, a negative out front, that essentially undoes each other, so I have the pieces I need. So I have a negative out front, negative sine x dx on top, cosine x on bottom, which in terms of u, negative sine x dx, that's du, over cosine, which is u. That's negative natural log absolute value of u, which what is u? Yeah, u is cosine. Now, every time you integrate tangent, you don't have to go through all of that. They show that if we have tangent u du, that integrates into negative, let's see, let me make sure, negative natural log absolute value cosine u plus c. So we had all the derivative rules for the trig functions, but we didn't, up until this section, we didn't have an integration rule for tangent, cotangent, cosecant, or secant. So now we have those in this section. I won't write all of those out. Those are on page 333. if this will go to that page. Let's do it the old-fashioned way. So those are integration rules for our 6 basic trig polynomials. So these two we already knew. Basically, the derivative of sine is cosine, so the antiderivative. Derivative of sine is negative, or derivative of cosine is negative sine, so hence this one. But the other ones involve natural law. All right, let's do a definite integral. Remember when we did integrals that didn't have numbers here or here, we called those indefinite integrals, which were just antiderivatives. But when we have numbers there, we called those definite integrals. Let's see. Let's look at this one. So just a little quick refresher. You might remember that when we do a definite integral, we want to find the antiderivative of our function. Once we get the antiderivative, then we substitute this number into the antiderivative, this into the antiderivative, and subtract. So the question is, well, what is the antiderivative of that? So I'm just going to come over on another page for now. Any suggestions on what we let u be? What's the degree of the denominator? 1. What's the degree of the numerator? 0. If the degree of the numerator is 1 less than the denominator, then try to let your denominator be u. Because when you take the derivative to get du, you're going to go down a degree, if it's a power rule. Notice if we let that be u, then what is du? 3 dx. We don't have any extra variables that are beyond what we need. So basically, this is u. We need 3 dx. We actually have 5 dx. Well, we can fix that pretty easily. Pull the 5 out front. If we want 3 dx, we got the dx, what do we need inside to make 3 dx? We need a 3. If I put a 3 inside on top, what do I need out front? Yeah, I need a 3 on the bottom out front. So the denominator, we called that u. 3 dx, that's du. So when we substitute, we have 5/3 times the integral du over u, which is 5/3 natural log absolute value of u, which our u is what? 3x plus 1. And if it were an indefinite integral, we would need a plus c. But when we have a definite integral, we're substituting numbers in, so we can leave our plus c off. So our antiderivative is this, and we need to evaluate that from 0 to 5. So antiderivative, we're going to plug in our upper limit, our lower limit, and subtract. So we're going to substitute a 5 in. We're going to substitute a 0 in. And whatever we get, we're going to subtract. So we have 5/3. Let's see, 15 plus 1, that's 16. For the second one, 3 times 0, that's 0 plus 1. If you wanted to simplify that, anybody remember what natural log of 1 is? 0. Natural log of 1 is 0, so 5/3 times 0 is 0. So the exact solution is that. Or if we want a decimal approximation, we could do 5/3 times natural log of 16, roughly 4.62. I'm not going to do one like this today, but let me make a reminder. Those of y'all that had me for Cal1 last semester, when we went through this section, this is called an improper fraction. And the thing that makes this an improper fraction is if the degree of the numerator is larger than the degree of the denominator. You might remember from just basic fractions, if we have a fraction where the numerator is bigger than the denominator, that's called improper. And the way we change it to a proper fraction is we divide it. 4 goes into 9 twice. We're left with 1, so 2 and 1/4. We do the same thing here. If this is improper, if we want to change it into a proper fraction, we divide that out. Now, if this would have been a binomial on bottom, we would basically have to use long division to divide that out. Since we have a monomial, we can actually do this shorter. To divide this out, we take each term divided by the denominator. We can simplify that. X squared, x cubed reduced, leaving us x. This simplifies, leaving us 8 over x. And when we have things added or subtracted, we can integrate separately. We can integrate this. That's just the power rule. We can integrate this. If you come over to the sign and integrate that, that's basically dx over x. You have a multiplicative constant with it, but dx over x or du over u, that integrates into natural log. So just a little trick there that I wanted to remind you of. We have an improper fraction, bigger degree on top. To integrate it, we need to rewrite it first by dividing it out. two other things I'll look at real quickly. One of them is to remind us what integration and application of integration. If we look at the function y equals 1 over x, I guess we'll graph it here. We look at y equals 1 over x. We have a function that does this. And back in chapter 4, our first section was just, well, how do we get antiderivatives? But after we looked at antiderivatives, we started looking at area. And if we want the area in this region, if this function is positive in this whole region, then the exact area between that curve and the x-axis comes from integrating that function. That function is 1 over x, integrating it over our interval. Our interval starts at 1, goes to 2. So if we want the area of that shaded region, integrate our function from 1 to 2. Now, we discussed last semester that if in this interval our function ever goes negative, that there's some special things we have to do. If we were to integrate from here to here, our y values are negative. We said that would actually give us a negative area for that, where that doesn't really make sense, a negative area. But as long as our function is positive, then when we do this definite integral, the value we get is equivalent to that area. What is this integral? What's the antiderivative of this? Yeah, that's just dx over x. The antiderivative is natural log absolute value of x. We're evaluating that from 1 to 2. Which means we substitute a 2 in, substitute the 1 in. Caleb reminded us that natural log of 1 is just 0. So the exact area under the curve there is natural log 2. If you want that as a decimal approximation, that area is approximately 0.69. So just a little reminder of one application of of integrals, definite integrals. The last thing is one other application, and some books have this, some don't. And this book has a problem similar to this. I haven't found one exactly like what I want. But basically, a lot of things in nature, the rate at which the population changes is proportional to the population. For example, if you're carbon-14 dating, the rate at which the radioactive isotope carbon-14 deteriorates or breaks down is proportional to how much carbon-14 you have. The more you have, the faster it decays. The less you have, the slower it decays. Y'all probably all heard the little, I don't know, trick question or riddle. If somebody offers to pay you 1 penny on the first day and 2 pennies on the next day and 4 pennies on the next day and double your pay each day, would you work for them for a month if each day they doubled your pay? Anybody willing to do that? You ever? Basically, what you would get paid by the end of the month is 0.01 to the 30th power. I matched the wrong button somewhere. Not 0.01. 2 to the 30th power. That's cents, so divided by 100. Make about $10 million doing that. And what happens is, on the second day, if you're doubling a penny, you're not making a lot more. But after a while, like on the next to last day, you're making $5 million. So then when you double that, you're still only doubling it. When you doubled a penny, that wasn't a dramatic increase. But when you double $5 million, it's a pretty big increase. Well, that's kind of what we're saying here. Our rate that we're changing is just based on how much we have. In that example, we doubled how much we had every day. When we had a lot, then we were changing quickly. I mean, changing from 5 million to 10 million, that's a big change. Where when we had just a little, 1 penny, changing from 1 penny to 2 pennies, that's not much. So our rate of change is proportional to the population, how much we have. If you think about it, if you go out and buy a pair of rabbits, or pigs, or chickens, are you going to have, is your population going to grow faster if you just have 2 of them, or is it going to grow faster if you have 20 of them? It's going to grow faster if you have 20 of them. The more you have, the faster your population is changing. So, let's suppose we have some situation so let's call y our variable. So the rate at which y is changing is proportional, so just some constant times how much we have. So y represents how much we have. Let's come up with a function that tells us, okay, if we have how at a certain time, what's our population? So basically, under this restriction that the rate is proportional to the population, let's find the function that tells us what our population is at a particular time. So this is just a basic example of a differential equation. Let's move dt over. How would I get dt on the other side? Basically multiply both sides by dt. So we have dy on the left, ky dt on the right. No jokes. Okay, well, sorry. We have dy on the left, so if we have y anywhere, we want y on the left with it. We have dt on the right, so if we have another t somewhere, we want t on the right. So how do I get y on the left? How do I get this y over here? So dy over y equals k dt. Now k is just our proportionality constant. We don't know if our population is doubling, tripling, going up by a factor of 1.4, going down by a factor of 1.3. So this is just a proportionality constant. Once we have our variables separated, now we can integrate. What does dy over y integrate into? Natural log of y. Now, since we're integrating both sides, we only have to put a plus c on one side. So let's save our plus c for the right. Our variable of integration on the right side is t, so k is basically a constant. So if we integrate the constant, remember we pick up our variable. Then we have a plus c. Now technically that is the antiderivative of both sides, but remember that y represents our population. So can y ever be negative? No, y can't ever be negative, so really there's not a need for those absolute values. Okay. We want to solve this equation for y. So we want y by itself on this side. Anybody have a suggestion of what we can do to both sides to get rid of the natural log here? Yeah. Exactly. Do e to that power on both sides. Remember from pre-cal, e and natural log are inverse operations, inverse functions. When we have inverses, those cancel each other. That leaves us y on the left, this on the right. We can leave it like this, or let's do this. Let's call this e to the kt times e to the c. Now, why multiply? Back from algebra, if we multiply like basis, what do you do to the exponents? Add. Multiplying like basis, we add the exponents. So if we have exponents added, we can write that as a product of like basis. These are the same thing. T is our variable. Is E a constant or a variable? E is a constant. Is C a constant or a variable? That's a constant. If I take a constant and raise it to a constant power, would you say that's a constant or a variable? A constant. If I take a number that's not changing and raise it to another number that's not changing, that entire piece is a constant. So let's just call that capital C. Now this part is variable. Our exponent varies. This is a constant, this is a constant, but if any part is a variable, then that varies. Now that formula, that equation might look familiar. Pre-cal, if you did continuously compounded interest, this is the formula you use. It's basically an exponential growth, exponential decay formula. And you use that anytime that the rate at which your population changes is proportional to your population. So, in the past, in pre-Cal, you were just given that formula there. That's where that comes from integrating this differential equation. All right, we'll stop there. When I get back to my office, I will see about getting y'all's WebAssign page set up. I will email y'all, or not email, I will put a list of instructions to register for our section in WebAssign. I'll post that on Blackboard. I might email it as an announcement, so when you get that email or see that announcement in Blackboard, you'll know that it's added on there. We'll do that. Those of y'all that have lab, we won't stay all the time, the whole time today. We'll meet for a little while. 3:30. Yeah.